Hey there everybody, welcome to a video on Euler's method, sections 2.7 and 8.5. Euler's method is a classical, really cute little technique for solving differential equations that requires just a little bit of Calc 1 review. So this unit I've broken into two videos. The first video does that little bit of Calc 1 review, and then in the second video on these sections we'll get back to Euler's method and the differential equations. So what is the point of these sections? Why are we covering them? Well, when we get to epidemic models, we will be confronted with systems of DEs that we cannot solve. The thing is, though, once we write these systems down, we will want to solve them. So what do you do when you have a differential equation or a system of differential equations that you want to solve, but you can't solve? One thing you could do is give up, of course, but what if you're not allowed to give up? What if we really do want to make predictions about disease spread? Well, you can use sort of numerical techniques, approximating techniques, and one of them is called Euler's method. Euler's method can, quote, solve these systems. I'll explain why there are quotes around here in a second. But basically, if you have a DE or system that you can't solve, you can punt it off to Euler's method, and it will solve them for you in some sense. That's what we're going to do with epidemic models. We're going to hand these models off to Euler's method in a Python script and have the Python script do it for us. The reason I want to cover these sections is because I don't want the Python script to be a complete black box. I want you to have an idea of what's happening there. So as always, right, there's some sort of tension in a class like this. Do we prove everything? Do we explain everything? And the answer is no. But on the other hand, I don't want things to just be complete mysteries either. Okay, so we're covering these sections so you have some idea of what that Python script is doing. So here's the motivation for these two sections. Suppose I handed you this differential equation, this initial value problem, I guess, and asked you to solve it. What would you do? You should probably do this. You should probably shrug and say, I don't know, man. Because if you think about it, we don't have the tools to solve this initial value problem. This differential equation looks kind of like differential equations we covered in Chapter 2, but it doesn't fall into any of the categories we solved then. This is not first order linear. The y is squared. It's not separable, it's not exact, so on, right? So this differential equation is not solvable by previous tools. So if I ask you to solve this, that is not a fair question, right? It's not a fair thing to ask. So after you shrug and look at me with an annoyed face, right? Suppose I come back and said, oh, sorry, I should clarify. When I said solve this initial value problem, what I really meant was, can you sketch a graph for me that's reasonably accurate? That's sort of a different and maybe easier thing to do. So I'm not asking you to tell me y equals stuff, right? Y equals sine t times e to the t, whatever, right? None of that. I just want a graph of y. And by the way, we know where that graph starts. At time 0, it starts at 1. So from that point 0, 1, can you estimate for me how the graph goes? Euler's method exists for this purpose. You have a DE, you don't know how to solve. Euler's method can sketch a graph for you. And that is why there were quotes around this solve. Okay? Euler's method does not exist to tell you like, oh, y equals this. It exists to draw a graph. So that's the punchline of these two sections. Euler methods exist to sketch graphs of solutions of first order DEs or systems of such things. The epidemic models we will do in the next unit are systems of first order DEs. We are not going to get formulas for any of the functions. We are simply going to ask Euler's method to sketch graphs for us. So let me now illustrate the basic idea of Euler's method. The basic idea comes from the first month or so of Calc 1, and it's a really nice idea. So suppose you have this function here, x squared plus 1, and suppose you had no idea what the graph of that function looked like, except I'll tell you a couple things. I'll tell you that 0, 1 is a point on that guy's graph. We all agree with that. And suppose also you know some Calc 1, by which I just mean you know what derivatives are. So given some basic Calc 1 knowledge and this single point on that guy's graph, could you sketch a function as we move to the right for x greater than 0? And the answer is yeah, right? Because what does Calc 1 let you know? Calc 1 lets you know about slopes of tangent lines. But what are slopes of tangent lines telling you? They're telling you the direction that a graph is moving in. Okay, so if you have a start point of your graph, and you know the direction that the graph is moving in for any x value, you can estimate what the graph looks like. So you can just sort of stitch tangent lines together to get a sketch of this dude's graph. How does that work? Okay, so here's the Calc 1, right? 0, 1 is a point in that guy's graph. We know some Calc 1, so we know the derivative is 2x. These are our directions, right? For a given x value, you can plug that x in there and figure out what direction the curve is moving in. Okay, well, you know that when x equals 0, the slope of the tangent line is 0. So if you're at this point 0, 1, and you want to move to the right a little bit in the direction the curve is moving, you would take a strictly horizontal step, wouldn't you? There'd be no verticality to your step because the rate of change is 0. The slope is 0. Okay, well, suppose you decide I'm going to take a step of size 1 to the right. So following along a tangent line of slope 0, you would then be at this point. If you started at 0, 0, and you take one step to the right with no movement vertically, you would be at point 1, 1. So let me just show you this visually. Okay, this point right here, this is the point 0, 1. Here is the tangent line at the point 0, 1. So at x equals 0, right, the curve x squared plus 1, that guy's graph, it is moving like this, instantaneously moving like that, right? Certainly not globally, but instantaneously at x equals 0, that's what the curve is doing. So you could just like travel along this line for a little bit if you wanted to. So let me do that. I'm going to plot the point 1, 1 right there, okay? So I've taken kind of a big step, but anyway, if you want to get an idea of what x squared plus 1 is doing, starting at x equals 0, you can just take a step to the right a little bit. This doesn't look like a little bit. I've maybe gone too far, but whatever. You can decide how big of a step you want to take. Okay, so that's all I'm saying. You have a point, you got a tangent line, you travel along the tangent line for however far you think is appropriate. Okay, so I'm going to go back here. Okay, so now you're at the point 1, 1. Well, what if you want to take another step to the right? And you want to sort of move in the direction of the graph of x squared plus 1. Well, now, if you're moving from x equals 1 to x equals 2, since you're at x equals 1, you can plug x equals 1 in here, and you get a slope of 2. Well, what does that mean? That means if you take one step to the right, you're going to go up by 2, approximately, right? That's one way to think about these tangent line slopes. If you take one step to the right, you'll go up by 2 approximately. So if you're already at the point 1, 1, and you're going to take one step to the right and 2 steps up, you're going to land at 2, 3, and so on. You can just keep doing this over and over and over again. So let me keep my point. Okay, so if I'm at the point 1, 1, and now I have a line of slope 2 going through that point, there's that line, and here's my point 2, 3. Okay, so I've traveled along this tangent line, and I've traveled along it for an x step of size 1. And so on. So I could keep doing this. Let's see. My next point, if I take this line out, my next point will be 3, 7. Okay? If I were at x equals 2, right, x equals 2, the slope now would be 4. So if I take one step over, I take 4 steps up. Right? If I'm at x equals 2 and the derivative is 2x, my slope would be 4. So anyway, if you just start stitching together these points, so imagine drawing a straight line from there to there, from there to there, from there to there, you would start building a graph. And that graph is not totally dissimilar from the actual graph, right? This is the actual graph. Now, clearly, these blue dots aren't like a perfect approximation of this, right? There's, at the scale I'm at, right, there's a pretty big gap between where these blue dots are and where this black curve is. However, I mean, it's fairly close globally. I mean, if I zoom out, you see, you zoom out, it's not so bad, right? It just depends on what sort of scale you're dealing with. If you kept drawing these blue dots, they would just keep flowing in the direction of x squared plus 1. And again, if you sort of connect them via straight lines, straight line there, 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 you get this sort of piecewise linear curve that globally looks like this parabola. That's the idea of Euler's method. That if you just know some derivative information meaning slopes, right, and you have some start point like that, you can just kind of like stitch together tangent lines. So let me just point out that previous slide is exploiting this little fact from Calc 1. The change in y, if you're at a particular spot right now and you want to know how much does y change, the change in y is the slope information at the given x value you're at times the change in x. That's what this tiny little compact equation is saying. If you're at a particular x value right now and you want to know how much y is going to change, if you take a step to the right of size dx, okay, the change in y will be the slope information at x times whatever that step size of x is. So anyway, all I'm saying is if you're here, you're at xy, and you want to take a step of size dx to the right, on the previous slide dx was 1, but you can let dx be whatever, you will take a step of approximately this size in the y direction. Again, this is just like the first month of Calc 1. So just to give you another example of that, the previous slide took steps to the right of size 1. Well, what if you decided to take smaller steps? Because we said at the beginning, right, this first little point I have here, that point, maybe I stepped too far along this horizontal tangent line here. Maybe I shouldn't have stepped so far, right? So let me now do step sizes of a half. And look at how that goes. So 0, 1 is still our start point, and we still know that the derivative is 2x. So if we're at 0, 1, and we take a step to the right of size a half, I'm just going to use this formula here, right? F prime of 0 goes here. The change in x, so the x step size goes here. Right, so you're multiplying by a half. So if you plug in 0 into the derivative, you get 0. So this quantity here is 0. 0 times a half. So if you're at 0, 1, and you want to know, oh, if I move to the right a little bit, if I move to the right by a half, how much do I go up or down? Like, what's the change in y? The answer is no change in y. This should not surprise us because, again, we're along that horizontal tangent line, that y equals 1 horizontal tangent line that we were on before. So anyway, so we take a step to the right of size half, and we end up there. We travel along a horizontal tangent line for a step size of x equals half. So that's now like our second point on our graph. We already knew 0, 1 was on there. Here's our second point. Well, what if you're at that point and you want to take another step to the right of size a half? Then again, we know change in y is f prime of our current x value times our x step size. So you plug a half in here and you get 1. So you get 1 times a half is a half. So if you're going to move from 0.51 to now 1 something, right? You're moving from 0.5 to 1 on the x-axis. You're going to go up in the y direction by 0.5. So you're going to go from y equals 1. This is the change in y. So going from y equals 1 to now y equals 1.5. Okay, so now you're at this point. If you're at this point and you want to keep going to the right to get more points, you take another step to the right. Now the change in y is f prime of 1 because you're here now, right? You're at that point. So this derivative number changes as you move, right? So now the change in y is f prime of 1 times a half. So what is f prime of 1? It is 2. So you do 2 times a half is 1. So if you were at that point, 1 comma 1.5, right? We know that the y is going to change by a positive 1. So we get a 2.5 right there. And the x, again, changes by a half. X is always changing by a half. The real question is what happens to y. Okay, so if you take another step to the right, you can keep doing this over and over again. Okay, so here's the last one. If you're at this point here, you take another step to the right. Now you do f.5 of 1.5 times 1.5, times a half, and you'll get 1.5 as the change in y. So moving from this point here, you would land yourself at this point here. The x changes by a half, and the y changes by positive 1.5. Let me just show you these points being plotted. These are for step sizes of a half. Let me zoom in just so you can see. Zoom in like that. Okay, so my blue points are still there, right? The blue points were an okay but not great approximation of what the curve was doing. Now let me put in some red points. The red points will be from step size of half, right? So that point there, see it's halfway over to this point 1, 1 right here. And then the next point from step size of the half was that point. This is 1 comma 1.5. Then the next point was 1.5, 2.5. The next point was 2, 4, and so on. So I have the next couple going here. So notice the red dots, if you were to connect them by lines, right? A line there, line there, line there, line there. It's piecewise linear. The linear pieces are smaller because your step size is smaller. Also notice if you were to connect the red dots, you get a better approximation of the actual curve than if you connected the blue dots. So in general, the smaller steps you're taking, the smaller the size of the step, the better an approximation you'll get of this curve. Okay, so let me now zoom out. And you can start to see, right, depending on your scale, the red looks pretty good, doesn't it? Better than the blue anyway. Okay, so that is the idea of Euler's method. Again, it is just basic Calc 1. It runs on this little factoid from Calc 1, that dy over dx equals f prime. So if you can treat that like a fraction, you scoot that dx over there. Yeah, the smaller the time step, the more accurate your graph will be, where the time step just means how far are you stepping in the horizontal direction. So here's an exercise for you. So you should pause the video to do this. You should estimate f of 3 for this function, x squared plus x minus 1, given that f of 0 is negative 1. Use 2 different step sizes to do this estimate, so you should get 2 separate estimates. So pause this video, and I will see you in a second. All right, so that was a second of my time. I'm not sure how long that took you, but let's walk through one of the solutions. We know the derivative is f prime is 2x plus 1. So here are the computations for step size 1. So you're at 0, negative 1. The change in y is f prime of 0 times 1, which is 1. Here's your step size, right? F prime of 0 is 1. So you have 1 times 1. So what does that mean? The x increases by 1. The y also increases by 1, right? You go from negative 1 to 0. So 1, 0 is my next point. Okay, so now I'm at 1, 0. I just iterate this process, right? F prime of 1 times 1. F prime of 1 is 3, and then times 1 is still 3. So as you change the x, you go from 1 to 2. As you change the y, you have to increase the y by 3, so you get 0 plus 3 is 3. So now you get 2, 3. From point 2, 3, the change in y is f prime of 2 now times 1, because x is now 2. F prime of 2, what is that? 2 times 2 plus 1 is 5, so 5 times 1. Okay, so in moving from 2, 3 to your next point, you increase the x by 1, you increase the y by 5. So you go from 3 to 8. So we estimate, with time steps of size 1, we estimate that f of 3 is about 8. If you do the same thing with time steps of size 1/2, you should have now needed 6 calculations, right? Because you got to take little half steps to get your way to 3. And you should get an estimate like this, 9.5. So of course, we know what f of 3 is, right? F of 3 is what? 3 squared plus 3 is 12 minus 1 is 11, right? So 9.5 is a better estimate of 11 than 8 is. So as we've already seen, if you want to do smaller step sizes, you'll get more accurate estimates. Okay, so I'm going to stop this video here. In the next video, we'll pick up with the differential equation we started with. We will now apply Euler's method to differential equations, not these sort of toy examples from Calc 1, where again, this all seems kind of unnecessary, doesn't it? Because we know what this function is. We could just graph it, you know? So this all seems kind of pointless. But the reason I'm doing this is to illustrate what we will do with differential equations in the next video.